Nothing makes me happier these days than a new language version or major technical release. While we are drowning in the AI slop swamp, engineering teams are still doing excellent work, so today we are celebrating the release of Go 1.27.
Object to the test!
And this is a surprisingly substantial release, with changes across the language, runtime, tooling, and standard library. It even introduces generic methods, which means Go developers have apparently decided that generics are no longer an existential threat to simplicity. Before Go 1.27, only top-level functions could declare their own type parameters. A method could use type parameters already declared by its receiver, but it could not introduce new ones. For example, if you had a generic box containing one type and wanted a map operation that converted its value into another type, that operation had to be a package-level function. But with this new release, the method itself can declare the new type parameter. I know this syntax might feel overwhelming at first, so let's quickly unpack it. This first part is the method receiver, meaning the map function belongs to a box containing a value of type t. UUID introduces a second type parameter for the value we want to produce, and any means that u can be any type. The method receives a function called transform as a parameter, which takes the original t value and converts it into a u type. Finally, box of u is the return type, so the method applies that function to b.value and places the result inside a new box. In simple terms, because I know this might be a bit confusing, map can take a box of type int and transform it into a box of type string without losing type safety. This keeps the operation attached to the type where developers naturally expect to find it and makes generic APIs less awkward, but there is still one important restriction. Interfaces cannot declare generic methods, and generic methods cannot implement interface methods. As we all know, a programming language is more fun if it has more exceptions than actual rules. And this is funny because Go doesn't actually support exceptions. Type inference has also been expanded. When Go already knows the expected function type, it can now infer the type argument of a generic function inside composite literals, explicit conversions, and channel sends. This removes more of the repetitive type information that made early Go generics feel slightly bolted onto the language. Struct literals also became more convenient. Fields promoted from an embedded struct can now be initialized directly. Previously, you had to explicitly construct the embedded base value. Granted, this is a small change, but these small reductions in ceremony are exactly what improve a language without turning every release into a complete redesign. The runtime also received a new size specialized memory allocator. For small objects below 80 bytes, the compiler and runtime can use allocation paths specialized for the exact object size. According to the Go team, this can reduce the cost of these allocations by as much as 30%, producing an overall improvement of roughly 1% in allocation-heavy programs.
Not great, not terrible.
The good news is that you do not need to change any code. Existing programs simply become faster after recompilation, which remains my favorite kind of optimization because it requires absolutely no personal growth. Go 1.27 also makes Goroutine leaks easier to find, since the experimental leak detector introduced in the past version has graduated into a regular profile. A Goroutine leak happens when a Goroutine becomes permanently blocked, perhaps while waiting on a channel that nobody can ever write to or read from. The application may continue running, so these bugs can remain hidden while leaked Goroutines slowly accumulate and retain memory or other resources. The new profile performs a garbage collector-backed analysis, identifies Goroutines that can never make progress, and reports their stack traces. Goroutine labels can now also appear in panic traces, secret dumps, and runtime stack output, making it easier to connect a blocked Goroutine to a particular request or operation. But what's really exciting is that the standard library has received one addition that Go developers have been requesting from day one, a UUID package. This new package can generate and parse UUIDs according to RFC 9562. It supports random version 4 UUIDs and time-ordered version 7 UUIDs, which are particularly useful as database keys because values created close together also sort close together. The new JSON encoding library is also available without an experimental build flag now. The implementation has stricter defaults, configurable options, better streaming support through JSON text, and fewer of the behavioral problems that could not be fixed in the original package without breaking existing software. More importantly, the original encoding JSON package now runs on top of the version 2 implementation while preserving its old behavior. Existing applications receive faster unmarshalling without having to migrate immediately. If something does break, the original implementation can temporarily be restored with a flag. Remember that the new API does contain some intentional differences. Version 1 always sorts map keys while encoding JSON. Version 2 skips that work by default because sorting costs time and most applications do not require deterministic object ordering. Go 1.27 also adds experimental SIMD support. SIMD allows one CPU instruction to process multiple values simultaneously, which is useful for cryptography, image processing, compression, numerical workloads, and other code that performs the same operation across large arrays of data. The new SIMD package uses vector types whose width depends on the target hardware, so the same Go code can therefore use the available vector instructions on different processors while falling back to a pure Go implementation when the hardware lacks them. There is also a lower-level ArcSim package for architecture-specific instructions when developers need more direct control. SIMD is actually a really interesting concept. It stands for Single Instruction, Multiple Data, and the basic idea is that a CPU can perform the same operation on several values at once. Imagine that you need to add two arrays containing 8 numbers. With normal scalar instructions, the processor conceptually loads one pair, adds it, stores the result, and repeats this 8 times. With SIMD, it loads several numbers into a wide vector register and adds multiple pairs using a single instruction. Depending on the processor and the data type, one instruction might process 4, 8, 16, or even more values simultaneously. This matters because many performance-heavy algorithms repeatedly apply the same operation to large amounts of data. Image processing changes millions of pixels, compression scans enormous byte sequences, and cryptographic algorithms repeatedly add, rotate, and XOR blocks of data. SIMD allows these operations to use much more of the processor's actual capacity instead of handling every value individually. The cryptography packages continue preparing Go for a future in which quantum computers finally become useful, so we now have algorithms implementing post-quantum digital signature standard with integration into Go's TLS package. On top of everything else, there are also several practical tooling improvements. GoTest now checks whether your code uses standard library APIs newer than the Go version declared in your Go mod file, helping you to catch the classic situation where everything works locally and immediately fails inside an older CI environment. The godoc command can retrieve documentation for a specific package version, gofix includes more automatic code modernizers, and gomod tidy consolidates scatter dependency declarations into standardized direct and indirect require blocks. And before wrapping things up, here is your awesome trivia for the day. Two of Go's original creators, Rob Pike and Ken Thompson, also created UTF-8. In September 1992, while working on the Plan 9 operating system at Bell Labs, they sketched the encoding on a placemat in a New Jersey diner. Thompson outlined the bit patterns, they returned to the laboratory, and began implementing it immediately. Within days, Plan 9 had been converted to use the new encoding. Ordinary English text and existing Unix tools continued working unchanged, while characters from other writing systems used multiple bytes. Its self-synchronizing design also allows software to find character boundaries from almost any position in a byte stream. Today, UTF-8 is the dominant encoding of the web, so two of the people behind Go also help determine how most of the world's text is stored and transmitted. If you liked this video, you should consider joining our community where I'm posting more dedicated content. Please don't forget to smash all the buttons and see you in the next one.